So like they're gonna be drunk. Yeah. Yes, yeah. Okay. Do we have a one? No. Oh, to get that thing working. Yeah. I'm just thinking about that. We're going to do it. My entire last 30 years. Yeah. Yeah. Oh, no.
Yeah.
When you do area with green stairs, so for the actual material like that, you could pick anything that results in
As long as Green's operator is 1, you can do it. And I think you're going to be hard pressed to find a better deal than that one.
that's fair. Yeah.
But yeah, I mean, so some books, to my great surprise, will use negative 1/2 y, comma 1/2 x. And it's like, well, it works, but you got fractions all over the place in 2 different terms. Like, what are you doing? Why? I don't get it. I have never seen anything simpler than this. It does it. Yeah.
That makes sense. So
Yeah.
it could just be anything, and then what's one, and then you just integrate that.
Yeah, that's the cool thing. And the other thing that's cool about this one is that there's a really cool formula for how to evaluate this line integral of x to y. If you got line segments, then you cannot. I mean, that's awesome, right? And so you pick some random other vector field, then you're going to lose this one, which of course is the thing that makes the actual arithmetic work in the next example. Yeah.
Thank you.
Sure. Oh, time to get started. Let's see. Sarah B, Claire, Matt, Luke, Jaden, Emma, Liza. Oh, there you are. You moved. Yeah. Stuart. Oh, there he is. Okay. Ethan, Manya, Olivia, Kishal, Diego, Darwin, Sean, Jules, Doa, Matthew, Colin, Emily, Rennick, Sarah T, McKenna. Didn't I see McKenna here a second ago? I could have sworn I saw her. Yeah, okay, I'm pretty sure. Yeah, right. Claire, Sarah B. Oh, and it's time to start. Okay, so let's dive in. Okay. Oh, okie dokie. So here's the new thing for today. It's really, I'm going to start off by giving you a different point of view on stuff we've already talked about. I think this is a really cool observation. Nobody ever showed me this, by the way. This is something that occurred to me when I was in my 30s, I think. I mean, so it's a kind of a weird observation, but I think it's extremely useful for visualizing things. So specifically, I'm going to revisit the fundamental theorem of calculus. And I know y'all know the fundamental theorem of calculus. It's not my point. My point is I want to give you a different point of view for the purpose of setting up a comparison between the fundamental theorem of calculus that we understand really, really well, and furthermore, that we can draw really good pictures of that expose everything. And these new theorems that we're learning, like Green's theorem, which is about weird things like circulation and circulation density, and it's hard to visualize what's going on. Okay, so here's the weird point of view on the fundamental theorem of calculus. I claim it's an accumulation and density theorem. It's not even that hard to see. There's this accumulating quantity called change that accumulates. I mean, right? If you're moving along some interval, if time is passing or in whatever way, there's some variable that's changing across an interval. And if, as that happens, if there's a function that we measure the change of at each little successive step along the process, the total change is the sum of all those little changes, right? So in fact, you can see this really easily in a picture. How much did the function change on this interval that I've got drawn here? Well, we can measure the change, no problem. You can look at that point is where it started and that point is where it ended. So we measure change by looking at the value of the function at those 2 points. And here it is. The total change is there. I've already got it in the picture and everything. There's how much the function changed. It changed this much. Yeah, but that's an accumulation. That's the grand total of, as I was moving along in the interior, as I was doing this, on each little subinterval here, I can talk about how much the function changed. So on that little subinterval, there was that little bit of amount of a change, right? And we can add that up over all the little subintervals. We've got little changes that happen as we go along. And the total of those changes is equal to the overall change, right? So again, not a deep idea. How much taller am I now than when I was 5? Well, how much did I grow every day, and add up how much I grew every day, right? Very relatable idea. Okay. So furthermore, there is an associated density that we can talk about. And again, this is going to seem really weird to talk about it as such, but the derivative, the integrand in the resulting integral, that is a density. It's the density associated to the accumulating quantity, our accumulating quantity of change. Okay, so we'll call this change density. Now, there's a lot of different ways to think about the derivative, and it's slope of the graph, and velocity as something's moving, whatever, various different interpretations. Interpreting as a density is not high up on a lot of people's lists. For the purposes of what we're doing here, it's the perfect point of view. So in particular, when you're looking at slope, sure, you can think of the slope as, let me pick a point. Let me pick a point, let's say about right there. And you can look at a tangent line, and you can make this little triangle. And you can talk about the rise over the run and think of that as slope. But try now, if you would, instead to think of this as the associated accumulating quantity of change happening in a subinterval divided by the size of that subinterval. It's change per unit size, quantity per unit size. That's a density. Everybody with me? Okay, so yeah. So you can think of the fundamental theorem of calculus then again as an accumulation and density theorem. And I make the following observation that you've already got written down here, but that while I view change by measuring it at the endpoints, right? That's where let me do it like this. I view change as happening at the endpoints because, well, that's where I see it. That's where I measure it. That's where you detect it, you might say. But where did the change happen? It's not at all subtle for me to say, yeah, well, the function changed. The change actually happened there in the interior. Well, of course it did. I mean, right, that's how things change slowly in process in the middle. They don't just, change is not something that happens on the boundary. It's just measured on the boundary. Everybody with me? Okay, so now let me give you an example of what you can do with this interpretation of the derivative as telling you, even though there's an overall change that you measure on the boundary, the derivative helps you identify where that change is happening. So here's a really, really easy observation. This function f of x equals x squared, yeah, it changes by 9 between 0 and 3, right? Trivial arithmetic, no problem. Where did that change happen? Well, it happened at a sort of all the way through in the interior in between there. But did it happen more so in some places and less so in other places? Well, yeah. Change density, the derivative, right? If you want to know whether more of that happened at x equals 1 or x equals 2, okay, well, plug in those points. Plug in x equals 1 and x equals 2 and see what those change densities are. And the change density is greater at that point. So another way to say that is the function is changing faster here. There's more of the, there's a total accumulation of change. Yes, more of it's happening here than it's happening over there. And algebraically, that's given away by the fact that the derivative is higher at 2 than it is at 1. Everybody with me? All right. Well, all of this stuff that I've said about the fundamental chemical calculus is true about Green's theorem. Different details. Circulation is what we're talking about. If I talk about the circulation on the boundary of this rectangle here, so there's circulation as I would measure it going around that rectangle, right? So I measure it there on the boundary. Is that where the circulation's actually happening? It's pretty tempting to say, yeah, because that's the intuition we have for circulation. Our intuition for circulation is brand new, right? We've spent our lives thinking about how stuff changes and viscerally experiencing it happening in process, namely in the interior of an interval, right? So that's extremely familiar. This is a brand new thing that we're kind of getting. So it feels like circulation happens where you measure it. But it's not really true. I mean, where is the circulation actually happening? And what's the cause, if you want to think of it this way? What's the cause of that circulation that we're measuring on the boundary? Well, it's happening because of what the vector field is doing in here. That's where the circulation's actually happening. And just if I can persuade you, I've already observed, of course, that circulation's an accumulating quantity. And so let's look in various different little places. Here's a little region over there. And I appeal to your intuition. If I were to measure the circulation, around that little box right there, I'd get 0. Because the vector field's constant over there. And along this edge here, I'm going with the flow. But along that edge there, I'm going against the flow. So positive on one side, negative on the other side, those are going to cancel. And on both of these edges, I'm going perpendicular to the flow. Dot product's 0. So just everything's 0. And I would get, so the circulation is 0 there. And likewise over here and over there. And, even as far down as there. And by the way, likewise down here, there's longer field lines. I'm getting more positive line integral as I go that way, but I'm also getting more negative line integral as I go the other way across the top. And they still cancel because over here, the vector field is again constant, different, constant, but still constant. So all of the along in here, all that's 0 as well. But if you now go into this gray area here, this is where you're not going to get 0. This is where you're going to get a positive value, because the vector field strength there versus there, a little different now. You can see the way the vector field is drawn here. It's the lower you go, the longer the field lines are to the right. Right there, you have some stronger field lower, weaker field above. So yeah, there's still a positive versus negative thing, but there's more positive as you go to the right across the bottom, and there's less negative as you go to the left across the top. And so there's some cancellation, but there's also some left over. And so you have a positive circulation there, and likewise here and there and there and there and there and there and there, and anywhere in this gray area, right? Positive circulation. So, okay, yeah, there is a grand total around the blue line, the blue boundary. Yeah, there's positive amount of circulation. Where is it coming from? Where did it happen? It happened in here. Okay. All right, now, how much happened where and how do I distinguish? Well, in the same way that the derivative is my change density and therefore literally tells me, yeah, there's more change happening here. Oh, there's less change happening over there. The derivative is the giveaway. Likewise, Green's operator here. If you were to compute Green's operator, if we were to write down the formula for this vector field and actually, write it down, what you would find is that over in this top region over here, you'd find that Green's operator was 0. And in this bottom region, you'd find that Green's operator was 0. And in this gray region in here, you'd find that Green's operator is positive. So Green's operator, by its values, will explicitly point and tell you where the circulation that you're measuring on the boundary is actually coming from. Yes?
What is special about that gray region?
Yeah, because this is where the vector field is changing, right? So the thing about this, this top sort of yellow, what I'm highlighting in yellow here, is the vector field's constant there. It's the same everywhere.
Oh, okay.
Right, but if you look at the little vector lines here, I'm making them longer in this gray region, and so that the fact that they are getting longer as you go down through the gray region, that's what's making Green's operator be positive there, as it's going to turn. And there's the algebra. You got to write down the algebra to confirm, make sure I'm right about this, but I am. That if you were to make such a vector field and compute Green's operator, it'd be positive there, because it's measuring circulation density and you can see the circulation being positive. Is that cool?
But there would be no circulation at the bottom.
Correct. Correct. Yeah, that's right. That's a great way to think about it. I mean, imagine a leaf. Imagine this is the flow of a river, and here's a leaf that's being pushed along, and it's being pushed equally hard on both sides. And so why would it spin? It's just going to flow straight across, right? Whereas by comparison, in this region here, it's being pushed harder on that side and softer on that side. And so it's going to be spinning, it's going to be moving to the right, but spinning counterclockwise.
But
Yeah.
the boundary does move in the same direction as the arrow.
The what now?
So like the boundary at the bottom, it's moving to the right. And
Yes.
the arrows are moving to the right.
Yes.
So it seems kind of counterintuitive with the operators.
Oh, well, I mean, you got to keep in mind what Green's operator computes, though. Green's operator is not just measuring what the field is. It's measuring how the field is changing in different directions, right? So here, the field is not changing at all. And so there's nothing to change. Yeah. Okay. All right. So I'm a big fan of this idea. So in other words, if you want to have an idea of what Green's operator looks like, right? and I make the assertion that it's telling you where circulation is happening because it's circulation density, right? I mean that in literally the same way that I mean that the derivative tells you where change is happening, because after all, the derivative is change density, right? So I know you're comfortable with this, right? That the derivative is telling you where change happens. Yeah, right, of course, absolutely. Well, Green's operator is telling you where circulation is happening. Okay, and likewise, by the way, this thing called divergence, right, that we saw last time, that's telling us where the flux is happening. And so here's the corresponding picture. Now, this is, again, the two-dimensional picture. For whatever it's worth, we will eventually see a three-dimensional version of flux and a three-dimensional version of divergence, but that's foreshadowing. So two-dimensional version of the picture. Where does flux get measured? Well, I measure flux across boundaries, right? How much is the fluid flowing outward across that boundary? So this is how you measure flux. Now notice this is a different vector field. This vector field is, again, it's got a lot of sort of constant sections. It's a constant there, pointing to the right. It's a stronger, it's a larger constant here, going to the right. And then it's kind of growing in this region in the middle here, right? Again, I claim if you look at this orange rectangle, and if you were to measure the flux across this orange rectangle, well, there's a large positive flux happening across that right edge. Right? There's a small negative flux happening across this left edge. So large positive, small negative. I mean, there's going to be a little cancellation, but there's still some positive left over. Of course, the flux is zero across the top and the bottom because the dot product is between two orthogonal vectors. So positive total flux, where is that flux coming from? Well, there's no flux happening here because there's just as much going in as there is going out. There's no flux happening over here because there's just as little going in as there is going out. The flux is coming from this gray region where, again, if you look at a little rectangle there, there's a little going in, but there's a lot coming out. That adds up to a positive, small, but positive amount of flux happening there, and likewise everywhere in that gray region. So what's the numerical tip, or what's the algebraic tip-off as to where and how much? In the same way that the derivative, in its interpretation as change density, tells you where change is happening, Green's operator in its interpretation as circulation density is telling you where circulation is happening. Well, divergence, thought of as flux density, is telling you where flux is happening. This orange flux that I measure on the boundary, where is it happening? It's actually happening in this green region in here. And divergence would indicate accordingly. If you were to construct this vector field and compute the divergence, that's where the divergence would be positive. Okay, so I think this is a nice point of view. A lot of good intuition can come, by the way, and this is a broad statement about math and probably other things as well, but let's keep it about math. If there's something that you understand really well, and I know y'all understand single variable calculus, fundamental theorem of calculus very well. If you can find a connection or relationship, analogy between the thing that you understand and the thing that you're learning, the thing that you're trying to understand. Once you have a connection, once you have an analogy, then anything you know about the theorem that you understand, you can translate over and say, well, what does that tell me about Green's theorem? Or what does that tell me about the divergence theorem? And what you understand in the easy context will help you understand analogous facts in the new context. And that's the purpose of this little discussion here. Okay. All righty. Yeah, so let's see this in action. I claim that Okay, well, so the question, we got a vector field given, and the question is asking, there is a circulation and there's a flux through a certain rectangle. And whatever those are, we don't really need to care about what they actually are. But for each of these, for circulation, for example, is more of the circulation happening at this point or at that point? I wanted to change the color. Which of these 2 points is there more circulation happening? Well, circulation is indicated by Green's operator. So we're going to compute Green's operator. There it is. There's Green's operator. You want to compare these 2 points? Okay, plug them in, see what Green's operator is. And Green's operator is, well, these 2 values. So which one of these is greater? Well, of course, that one is greater. And so that's the point where there's more circulation happening. And I know there's more circulation happening there because the circulation density is greater there. This is exactly the same argument, and I encourage you to try to, develop the same intuition that I claim there's more change happening here because the change density is greater. Same idea, different geometry. Okay. Likewise, by the way, with the flux, I mean, same vector field, same rectangle. I can talk about the amount of flux through that rectangle. Which one of these 2 points has more flux happening, more flux being created at? Well, flux is understood by divergence. Divergence is flux density. And so I'm interested in comparing these 2 points. Fine, plug them in, see what you get. The divergence is, well, these are the 2 numbers. Where is there more divergence happening? Well, there's more divergence there. So there's more flux being created also there. Everybody good? All right. Okay, so let's move along. So we're done with 6.2 now. We're going to go on to 6.3, talk about what they like to call conservative vector fields. Let me start with a complaint. A conservative vector field is a vector field that is a gradient of some function. Okay, well, how about we just call them gradient fields? Why do we need a new word? Call them conservative fields? They're gradient fields. We already had a word. Right, so I think that's silly. The reason that they like to say conservative is because there is a very important feature of these kinds of vector fields that allows for making an interpretation in physics that, in particular, you can define this concept called potential energy, right? And if y'all taken a physics class, you remember potential energy. So in order to make a meaningful definition of potential energy, you need this idea that comes out of the vector field being a gradient. And so conservative makes sense in the physics context because they're all about conservation of energy, because they're physicists and energy is what they're ultimately more interested in, right? So it's not a ridiculous choice, but for what we're doing here, I think it's unnecessary. So I'm going to use this term conservative just for sort of cultural purposes, because this is what you're going to hear out and about, as it were, when you're talking about these kinds of things. But I'm going to most of the time just call them gradient fields because that's explicitly what they are. Okay. Okay, so I'm going to start with the big theorem. The big theorem is called the fundamental theorem of line integrals. You'll note the analogy between this name and the fundamental theorem of calculus, right? In fact, they're shockingly similar theorems. So if your integrand is a gradient, then you can compute the value of the vector line integral as, well, it's f of b minus f of a, f being in particular the thing whose gradient is the integrand. Right, so in single variable calculus, this is an integral of a derivative is computed by looking at the difference of the value of the function at the endpoints. Okay. Everybody see how this is fun looking at calculus? I mean, certainly superficially, it looks exactly like the fun of looking at calculus. All righty. Different ways that one can prove this. As you all know, I'm a big believer in this idea of accumulation and density. So I want to point out first that as you are moving along some curve, change is an accumulating quantity, right? So now this, again, you have to think this through. How do we know that change is an accumulating quantity over path? Well, if I take the amount that whatever function I'm interested in changes on that first part of the path, and then if I look at how much that whatever function I'm interested in, how much does it change across the second part of the path, the sum of those two changes gives me the total amount that whatever function that is, the total amount that the function changed in going across that path. I mean, it's really easy to see if you don't if you're not comfortable with how changes kind of accumulate. You can observe that these two terms here literally cancel, right? That x1 term, it's positive as part of the computation of change for the first piece. It's negative as part of the computation of change for the second piece, and positive and negative, same amount, of course, and they cancel. Everybody good? Can't help but notice it's morally equivalent to what happened in Green's theorem, right? Where we had this edge in the middle, the opposite directions, same edge, they cancel. Same thing here. Here in the interior, opposite signs in the algebra, and they cancel. Same deal. Okay. All righty. So change is an accumulating quantity. By the way, my favorite metaphor for thinking about this is letting the function in question, whose change we're keeping track of, think of that as being altitude. Right. And so I always imagine if I have some path, I always imagine, okay, well, I'm driving along some mountain road and I'm keeping track of how altitude changes. And well, of course, the total amount of altitude that I gain is the sum over each little segment of the drive of how much altitude that I gain on each segment. Okay. There is a related notion of density. This is really a callback to chapter 2. No, I'm forgetting the numbers. No, 4. Chapter 4, right, where we talked about derivatives. That we have an easy formula for how to compute how much some function changes. And keep in mind, the big point of view on derivatives is the relationship between input changes and output changes. So if you move by some displacement dx, that's your input change, and you want to compute the corresponding output change, well, the relationship between input changes and output change, this is the derivative, whatever form is appropriate to your context here, dot product with the gradient. Okay. All right. So you can rewrite that, of course, dx is TDS. So if you really want to, you can think of gradient dot T as the density. And this, in fact, let me take the snark off that language. This is arguably the right way to think of the density here. The density, the relationship between output change and input change, the ratio of output change to input change is gradient F dot T. Okay. All right. So there's your density. So with this point of view, I mean, we can write down, here's a way to think about, let me just go ahead and zoom up, we can see it better. Think about the fundamental thermal line integrals, is that this integral which by the way, of course, is also integral of the vector field dot dx. But let's leave it in this form here. That integral can be computed as, well, it's f of b minus f of a. But I'm viewing it instead as changes in accumulating quantity. So change adds up over the entire curve, and then on each little piece, there is the corresponding notion of density, namely how much change per unit distance, how much change per unit size, and we call that change density. So again, it's a accumulation and density theorem. Everybody with me? Okay. So at this point now, I do want to try to change point of view on this just a little bit, and this is going to be really useful later, more than we can sort of anticipate now. But I do like to rewrite the integral like this. I've already made the observation long ago that among the many reasons that I like this notation better is that the differential tells me everything that I could possibly want to know about each little piece of curve. This dx vector is telling me both how long, by the magnitude of dx, how long that little piece of curve is. ds is wrapped up inside of dx. But also the dx vector is telling me how that piece of curve is oriented, whether it's kind of pointing that way or whether it's kind of pointing this way, or, a bunch of different ways that you could be going. Right? All of which matters. So it's all wrapped up into the dx vector. So if you want to think about the integrand, I mean, if we're going to write the integral like this, if we're going to therefore need to make an interpretation of the gradient by itself, what is the gradient? The term that I propose and use on a regular basis is oriented change density. So the idea is that it's a relationship between input change and output change. It's just that the input change isn't a scalar size. The input change, I'm recognizing that I'm not just changing by a distance, I'm changing by a distance in a particular direction. So this is an oriented notion of size in some sense. And notice that the object itself, the gradient itself, is a vector. So it itself is also oriented. The gradient is telling you not just how fast is the function changing, right, by the magnitude of the gradient. The gradient is telling you also in which direction is the function changing, right? It's also telling you which way is uphill on this mountain road that you're on at that particular moment. So I like this idea, oriented density, as a sort of attached to this sort of a rewrite of how we write the integrals. Okay, it's just semantics and interpretation, but of course these are the same thing. Okay, all right, so let's do one. Here's an integral that I might want to compute. Vector line integral. Got a vector field given. Got a curve given. And you can plug and chug. You could, I suppose, right? Not that you couldn't do it that way, but I will point out that if you do plug and chug, don't forget this is your x, and so that's going to go into there and into there, and this is your y, and so that's going to go into there and there. So there's going to be a fair amount of trig if you do the plug and chug. Again, which you can do, I suppose, but a certain amount of effort is going to go into that. Okay. Yes.
So we plug in cosine t for x and sine t for y, but then how do we get dx?
Dx is x prime dt. So yeah, just like we did back in 6.1, I guess it is. Yeah. So there's that whole, plug in the parameterization, pull back through the parameterization, and take a deep breath and plow. Yeah. Okay, so let me show you the slicker move. By far, the slicker move is to notice and I'll talk about this more in just a second, but hey, how about that? Check it out. That vector field is the gradient of that function, x squared, y squared. If I start with x squared, y squared and say, hey, take the gradient of x squared, y squared, then I get exactly this vector field. So when you look at the way this integral was written, it was written as integral of a vector field, but it's much nicer than that. It's actually integral of a gradient field. Conservative, right? But and it's literally explicitly an integral of a gradient. And so we could just use the fundamental theorem of line integrals. I can look at my curve and ask where it starts and ends. No problem. It starts at the point 1, 0. It ends at the point -1, 0. And so f of b minus f of a, right? We take our function here, whose gradient we're computing the line integral of. We plug in the endpoint, we plug in the starting point, we subtract. Fundamental theorem of line integrals tells us that that is f of b minus f of a, and bam, we win. I didn't have to deal any trig. Yes?
Where did statement 1 come from?
Oh yeah, no, that's yeah, quite right. Yeah, let me get to that in just a second. Yeah, no, it's exactly the natural next question to ask. Yeah. But before I get onto that, does everybody see how I use the fundamental theorem of line integrals here? And how extremely desirable, right? I mean, no trig integrals. No integrals. Right? So that was a pretty sweet deal. Okay, so yeah, great question. Where did this come from? Did my inner oracle just tell me this is the gradient of that, function? Yeah, so I swept that under the rug. There is a process for finding the function whose gradient you're looking at, and we're going to get to that in a little while. And there's just there's a couple of things I want to do first. So here's the bad news. We're accustomed in single variable calculus to, well, if you ever want to compute an antiderivative, there's tools and method, you just do it pretty much. And in fact, literally every continuous function in single variable calculus, every continuous function has an antiderivative. It's just a question of finding them and, integration technique, and it's annoying, but the point is you can always do it. That is not true with vector fields. In some sense, most vector fields are not gradients of anything. The way I like to say it instead, most vector fields do not have an, what I like to call anti-gradient. Okay. So we got lucky here. Not only were we lucky that it exists, but we were lucky that we I could eyeball and you could sort of strategize and see, hey, if I wanted to take a derivative and have it turn out to be that, get clever, right? And think it through. You can persuade yourself that maybe you could have dreamed this up. But that was also lucky. Okay, so again, we have a technique and that'll come later. Okay. So, related idea. I want to talk about something called path independence. If you compute a line integral, that line integral, of course, depends very much on the curve over which you're computing the line integral. Well, of course it does. If you want to know how much work it takes to accomplish a task, it matters a lot where you're going. Right? What curve are you pushing along? And if that curve goes uphill, that's important, right? As opposed to if it goes downhill. So obviously line integrals depend heavily on the curve. What is shocking is that sometimes only the endpoints matter. And I say it's shocking because, again, of course, I mean, the line integral depends so much on the curve. Don't we need to know the whole curve? I'm moving along the entire curve, right? Shouldn't the entire curve matter? Amazingly, sometimes only the endpoints. So this is a feature called Path independence. Our textbook likes to say has path independent line integrals. I think that's more words than necessary. I just like to say path independent. It's a very standard term. And a vector field is path independent if whenever you have two curves that start and end at the same points, those line integrals are always equal. If you could imagine such a thing, right? Imagine some vector field that is able to somehow work around the fact that you could take two very different paths to get where you're going, and along this path and along that path, totally different paths. They didn't even know which paths you were going to pick, but because they start and end at the same point, the line integrals are always the same. Super, super weird. First time I saw this as a student, I thought, well, that's not possible. There's too many different paths that start and end at the same point. There's countless, infinitely many paths that start here and end here. How could they all have the same value of the line? For example, this vector field here does not have the property of path independence, not even close. Because here's a couple of different paths. Let me start with the path C1 going like that. But on the other hand, now I get to the same endpoint by this C2 going like that. If I look at these two different line integrals, I get different answers. Along the first curve, along the blue curve, well, the vector field 0 on the first edge. And then on this side, the vector field's perpendicular to the direction I'm going, and that adds up to 0 on the first curve. On the other hand, I get 0 on the first segment of C2, but I get a pretty positive value along the second edge of C2. And so, look, you can write down some numbers and you can actually compute this up if you like. What you will find is that you get different answers. And because these answers are different, this vector field is not path independent. Because I've got two different curves from the same start and the same end, and they have different values, which again, as expected, right? How could I have the audacity to think that these two entirely different line integrals should just automatically be the same? It's unrealistic. Yes.
Can you explain how we know intuitively that there's a 0 or greater than 0?
Yeah, so you just got to look at the different chunks here. So let's look along this chunk. Along this chunk, the vector field is itself 0. So the integral of it will be 0. And along this chunk, you're going this way, but the vector field is that way. And so that dot product, f dot dx, well, dx is like this and f is like that. And so it's going to be 0 on that edge as well. Yeah. So the purpose of this example is to, it's kind of dramatic purposes here. I want to make sure that you, like I did, see how unobvious path independence usually is. But now check this out. Not only is it possible for a vector field to be path independent, but we know tons of them. We already know tons of them. Specifically, every gradient is path independent. Now, how do I know that gradients are path independent? Well, let's play the game. If I have on the one hand, this path there from A to B, and then on the other hand, I have this path here, C2 from A to B. How would I compute the line integral along C1? Well, I'm doing a line integral of a gradient, f of B minus f of A, fundamental theorem of line integrals. Okay, how am I going to compute along C2? Well, I'm doing a line integral of a gradient. So the line integral along C2 is, again, f of B minus f of A. So these two line integrals are both equal to the same thing, and therefore they're equal to each other. And it doesn't matter which two paths you pick. Any pair of points, any two paths that start and end at the same point, this argument works. So every gradient is path independent. How are we doing on that? Everybody good? All right. So it also goes the other way. And this is something I'm not going to spend time on proving, but not only is every gradient path independent, but it turns out as well that it's in the category of continuous, and I don't want to go off into regularity concerns. It's not what this class is about. Not only is every gradient path independent, every path independent field is a gradient. In fact, then, gradients and path independent fields are they're the same, exact same vector fields. Again, ignoring regularity issues with continuity, and we don't want to mess with that. Okay. If you're curious how to show this, that every path independent field is a gradient, if you have a path independent vector field, here's how you construct the anti-gradient. As it turns out, just define the integral between, fix sum A, define the integral from A to B like this, and it's a path independent vector field, so I don't have to tell you what path to use to get from A to B. It doesn't matter. It is literally path independent. So I can define this function, and if you take this function then and compute its gradient, you will get that path independent vector field F, as it turns out. So we have explicitly shown, I'm leaving out all the details. I really don't want to spend, this is details that are not really what this course is about, but neat fact that this, roughly speaking, this argument will show that every path independent is a gradient. Okay. All right. So here's another way to say path independence. This has some sort of neat applications. We're going to see later, well, not today, but we're going to see it later on. And that is, notice that if you have two line integrals being equal to each other, right? So the integral on C1 and the integral on C2 are the same. If those are the same, well, another way to say that is that their difference is 0. Okay. Well, yeah, but their difference, if you think about it, their difference is literally the curve that goes along C1 and then backwards along C2, because this minus sign, right, is what makes the orientations switch over on that side. So just a neat fact that you can rewrite, let's see here, you can rewrite the statement that these two line integrals are the same instead as the statement that this closed line integral, this line integral that starts, that goes all the way around, starts and ends back at the same point, is 0. So again, just a rephrase of path independence. An alternative definition of path independence is that on every closed curve, the line integral is 0. So one point of view you can take on that is it explains this, why Escher stairs are nonsense. I don't know if y'all are familiar. Probably y'all have seen MC Escher's art before, and he did a lot of illusions, art illusions, basically. And so here's, if you look at the picture here and you keep track of a particular line of people. So this guy here, right? He's clearly going upstairs, and he's going up. He's following these other people along sort of the outside, and they continue to go up, and they just keep going up, and then up, but then he's back to where he started, right? So on the outside edge of this picture, everybody's walking continuously uphill, which intuitively we know is nonsense, right? And then you look at the inside edge, everybody's walking downhill, 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 and of course that's also equally nonsense. So the way we can say that mathematically is to recognize that the way we keep track of whether you're going up or down is with the gradient, right? And if you want to measure how much someone ascends, is you do an integral of the gradient of the altitude function. Right? Well, here's the thing. Gradients are path independent. Path independent, we saw above, means line integrals have to be 0. And that's what's being violated here, right? So the line integral of the gradient of the altitude function must be 0 because of path independence. And Escher's picture here kind of violate that. They violate this rule here. And so that's why Escher stairs are impossible. Okay, and that's a good place to end it. So we will pick up here on Wednesday. Y'all have a good Monday. See you later. Yeah. Yeah, pleasant. Okay. All right, let's see. What am I doing? Stop.